Hello and welcome to yet another video of Cornerstones of Math. Last week I uploaded this Combinatorics video which involves 4x4 grid, and you have to find the number of cases to color the grid in a certain way. In this video I prepared another problem in a similar setting, but now with 3x3 grid. Consider a 3x3 grid made of 9 squares. You want to color 6 out of these 9 squares. The main goal is to find the number of cases in which 1, 2, and 3 squares are colored in each row regardless of their order, and 1, 2, and 3 squares are colored in each column regardless of their order. For example, if we color 6 squares like this, then from the perspective of rows, we have rows with 1 colored square, 2 colored squares, and 3 colored squares. And then from the perspective of columns, we have columns with 1 colored square, 2 colored squares, and 3 colored squares. Just like my 4x4 grid video, each row and column are considered distinct, so you don't have to consider the rotation or flipping of the grid. We also have this interesting bonus question. Can you generalize this to an n by n grid? Well, we'll find out, but let's first solve 3x3 problem for now. For the sake of the simplicity of the solution, we require a new notation to indicate rows and columns in the grid. Let R3 denote the row in which all 3 squares are colored. In a similar manner, R2 denotes the row in which 2 out of 3 squares are colored, and R1 denotes the row in which 1 out of 3 squares is colored. In a similar manner, we can also define columns C3, C2, and C1. Now let us get back to the 3x3 grid. We can count the number of cases as follows. First, we consider the process of choosing the spot for row R3 and color that row. This step is really easy. We simply choose one of these 3 rows and then color every square in that row. Therefore, there are 3 ways to choose and color the row R3. Next, we try to choose the spot for row R2 and color that row. Since one row is already taken for R3, there remain 2 rows which can be R2. Now, given that the spot for R2 is chosen, how many ways are there to color the row R2? We have to color 2 squares out of 3, so there are 3 choose 2 ways to color the squares. Therefore, there are 2 times 3 choose 2 ways to choose the location for R2 and color it. Now the third and final step for row R1. Given that rows R3 and R2 are already chosen, the only remaining row automatically becomes R1, so there is only one way to choose the spot for R1. The important question here is, how many ways are there to color this row R1? We color 1 square in row R1, but in order to satisfy the condition given in the problem, which is that 1, 2, and 3 squares are colored in each column as well, we color the square like this. In row R2, there exist 2 column indices indicating the positions of the colored squares. When we choose the square to color in row R1, we only choose squares from these 2 columns indicated by arrows. That is, we choose either this square or this square, but not this square where the corresponding column in R2 is uncolored. Why do we choose the square to color in this way? Well, if we choose to color this crossed square, then the number of colored squares in each column will be 2, 2, and 2. Hence, the grid will not satisfy the given condition that 1, 2, and 3 squares must be colored in these 3 columns. However, if we choose from one out of these 2 circled positions, then we can obtain a pattern in which 1, 2, and 3 squares are colored in each column. Therefore, there are 2 choose 1 ways to color the single square in row R1, and thus 1 times 2 choose 1 ways to choose the location for R1 and color it. In order to find the total number of ways, we need to multiply all of these, which gives 3 times 2 times 3 choose 2 times 1 times 2 choose 1. So 3 times 2 times 3 times 1 times 2, which gives us 36 ways. Now what about the generalized n by n grid? Well, we take similar steps as in 3 by 3, and you'll find it surprisingly easy. First, the location for row Rn, where all n columns in that row are colored. The number of ways to determine the location of Rn is n, the number of rows in a grid. And obviously there's only one way to color that row. So let's suppose that row Rn is determined. The next step is determining the location for row Rn-1 and coloring it. The number of remaining rows is n-1. And as for the ways to color that row, we have to choose n-1 squares or columns, hence the number of ways is n choose n-1. Here, coloring n-1 squares results in one uncolored column in that row, and that uncolored column will automatically become C1 in the end. Therefore, there are n-1 times n choose n-1 ways to locate and color Rn-1. Next, determining the location for row Rn-2 and coloring it. The number of remaining rows for Rn-2 is n-2. Once the location of Rn-2 is determined, we then choose n-2 columns that will be colored, but not from n total columns, but from only n-1 columns where corresponding columns of Rn-1 are colored. That is, we choose n-2 columns from only n-1 columns. As for the example in the figure, this means that this spot right here never gets chosen to be colored. If we choose and color the columns in this way, there will exist a column where row Rn-1 is colored, but row Rn-2 is not. This column will automatically become C2 in the end. And now you have perhaps realized the pattern. If we multiply them all, the number of cases is n times 1 times n-1 times n choose n-1 times n-2 times n-1 choose n-2, and naturally the next thing will be n-3 times n-2 choose n-3, and we go on until we have in the end 1 times 2 choose 1, for the very last row R1. Let us simplify this. If we multiply all non-combination parts, we have n times n-1 times n-2 times n-3 times so on times 1, which gives n factorial. Then we have the combination parts n choose n-1 times n-1 choose n-2 times n-2 choose n-3 times so on times 2 choose 1. Here, n choose n-1 is n, n-1 choose n-2 is n-1, n-2 choose n-3 is n-2, and 2 choose 1 is 2. Therefore, this part becomes n factorial, so we obtain the result n factorial squared ways. Now, when you come to think of it, this is actually a pretty intuitive result. N factorial is simply the number of ways to arrange n rows R1, R2, Rn And n factorial is also the number of ways to arrange n columns c1, c2, cn. Therefore, the answer being the product of these two seems plausible. However, simply multiplying these two does not explain how we can ensure that for every given random arrangement of these n rows, there has to exist n factorial arrangements of these n columns. That has to be guaranteed by coloring the squares in each row in a special manner that I just described, which happens to give n factorial ways of coloring. And when this n factorial ways of coloring is multiplied by this n factorial ways of arranging the rows, we obtain the answer n factorial squared. And that's all for this video. Thank you for watching. Please hit the like button if you enjoyed this video. And as always, I will see you in another video.